In today's session, we would be seeing the application of mice. The full form of mice stands out to be multivariate imputation through chained equation. So, what mice does is mice takes an incomplete data set, a data set having missing values, plugs in the missing value through a proper technique, and there are a lot of techniques for this plugging in or the imputation as we say. And once this has been done, it creates multiple number of complete data sets. For each complete data set, it performs the required analysis, and once the analysis is performed, it pulls to give an overall estimate. We would take a simple example, and the data set that we would be taking is the enhanced data set. So, this data set has 4 variables: age, BMI, hypertension and cholesterol level, and we are interested in modeling cholesterol level as a function of age and hypertension. But the problem is that we have missing data. So, we would use mice and see how we can use the function the functions in the package mice to analyze the data. The objective here is to see how we can implement multiple imputation in R. So, to implement multiple imputation in R, we need the 2 packages, the mice package and the VIM package. The VIM package is needed for the graphics that we would be generating. To start with, we would be using a data set called enhance. Now, this data set is in the library mice, and to get our details of this data set, one can use question mark mice, a question mark enhance. Now, the data contains 4 variables: the age, that is the age group, BMI, which is body mass index, HYP, which is the hypertension status, and CHL, which is the cholesterol level. The data is stored as a data frame, and the missing values are represented as NA. The objective here is to run a regression with the response variable as cholesterol level and the explanatory variables as age and HYP, hypertension status. Now, if we just to see the data, we can write head enhance, and once we write this head enhance, the output is given and we can see the values as well as the missing values are coded as NA. To inspect the missing data pattern, the missing data numbers can be visualized by using the function md.pattern of the data and input the data frame as the argument. So, if we give md.pattern enhance, we get age, hypertension, BMI, cholesterol level, and we have the numbers like 11111 and then 11011, so on. Now, what is the meaning of this? This says that there are 13 out of 25 rows which are complete. So, in this 13 rows there are no data which is missing. There is one row for which only BMI is missing, and there are 7 rows for which only age is known. The total number of missing values equals 27, while most missing values occur for cholesterol, and that number is 10. Another way to study the pattern involves calculating the number of observations per patterns for all pair of variable. So, a pair of variable can exactly have 4 missingness patterns. The first one happens when both of the patterns are observed, and it is denoted as RR. Then it might happen that the first variable is observed and the second variable is missing, that is the pattern RM. The third pattern is that the first variable is missing while the second variable is observed, that is pattern MR. And Then we have the fourth pattern and the final pattern where both are missing, and that is pattern MM. So, one can use the md.pairs function to see what is the pairwise pattern, and here we have used md.pairs and have stored the result in P, and typing P gives us 4 matrices which gives the pattern. So, for example, we have 14 pairs where hypertension and cholesterol is available, right. So, we have 14 where it is available. So, there are 3 cases where hypertension is available, but cholesterol is not. There is one where cholesterol is not available, but hypertension is available. And there are 7 where none of the cholesterol and hypertension is available. The R package VIM contains functions for plotting incomplete data, and in general it is a good idea to use this package to see what the patterns or the missing data patterns results in. So, we can compare the distribution of one variable within subgroups defined by others, and the pbox function in VIM does this. So, if we say pbox enhance pos equal to 1, we generate a plot which looks like this. So, this plot shows the distribution of age in the white box at the left hand side, and this distribution is split 3 times into 2 groups corresponding to the missing data in BMI, hypertension and cholesterol respectively, and in this case the distributions are quite similar. Now, we start our imputation process, and the main workhorse for imputation is the function called MICE. So, here we are passing the data set to that function. So, MICE enhance and storing it in imputation in the function called or in the object called IMP. Once we run this object IMP, we get the details of the imputation. The details of the imputation says that imputation was generated according to the default method, and the default method is the numerical data. The default method for the numerical data is predictive mean matching, and that is why it says PMM. For age, because there is no missing, there is a blank. The default number of multiple imputation is equal to 5. Now, if we really want to see what are the imputed values, for example, what are the imputed values for cholesterol, then we can use the command, the object name $imp, the variable which has been imputed. For example, here we have used IMP, which here both the object name and the name of the imputed data set is IMP, whereas the results are also stored in IMP. That is why we are using 2 IMPs, and then $cholesterol CHL, and it gives the cholesterol value imputed at each of the 5 cases or 5 times. So, for each row here corresponds to a missing entry in CHL, and the column contains the multiple imputations. The complete data is combined over the observed and the imputed data set. The first completed data set can be obtained by saying complete IMP, but because of lack of space, I have used the head command. So, we to just produce the first 6 observations. So, this is the imputed data set, but this is the for the first time imputed. Now, if one wants the second imputed data set, one can use complete IMP comma 2, and again due to lack of space I have used the head command, so that it gives the first 6 observations, and we see that in both the imputations the imputed values are varying. Now, we come to the original problem. Note that here, although hypertension status is a binary variable, we have been coding it as 1 and 2 as a continuous variable. And then if we run the complete case analysis, so by default the LM function runs a complete case analysis, and we would be using the LM function to investigate the relationship between cholesterol, age and hypertension. So, we run the LM command and just print out the summary, and we get the summary of the LM command, and we see that age has an effect, the intercept is significant. The age can also be treated as significant if we take the cutoff p value at less than 0.1, but hypertension is not. We can get the confidence interval by using the confint function. So, if we do that, we get the confidence interval for the parameters. So, for intercept and for age and for hypertension. Now, let us use the imputed data set. Now, what we can do is we create an object called fit, and with the imputed data set, that is why with the with function, and inside the with function it is the IMP, which is the imputed data set. The function that we are applying is LM, and what we are analyzing, we are regressing cholesterol with age and hypertension. So, LM explained by age plus hypertension, and we are storing it in fit. The fit object contains the result of 5 complete data analysis. So, if we type in fit here, we get the complete case analysis for the 5 the complete analysis for the 5 imputed data sets. So, for the first one, the intercept comes out to be the effect of the age comes out to be 17.46. While for the second imputation it comes out to be 11.33, for the third it comes out to be 23.87, for the fourth it comes out to be 27.3, and for the fifth it comes out to be 18.58. Now, we can use the pull function on the fit object to see what is the effect. We can have a more detailed effect by using the summary of the pull function. So, the summary of the pull function gives the estimate, the standard error, the t value, the degrees of freedom, the p values, the lower and the upper 95% confidence level or the confidence interval, and it also gives the FMI, which is fraction of missing information. The fraction of missing information is the proportion of variability that is attributable to the uncertainty caused by the missing data. Here note that while the age was significant with a cutoff of 0.1 in the complete case analysis, the age does not come to be significant for the imputed data set or for the results based on imputation. Also, the effect of age and the effect of hypertension is varying from what we get in the complete case analysis, that is by throwing away all cases where there is one or more missing observations. So, in today's session we have seen how to use the mice function in the mice package R to perform multiple imputation. We had taken a very simple example of linear regression in context to missing data and have shown how mice can improve the results. There can be a lot of difference in the interpretation when we use a complete case analysis versus a multiple imputed analysis or an analysis based on multiple imputation.